And yes, I can see it slightly off.
rather than up, 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 up.
I will try to draw my line a little bit better next time. Possibilities. It's going to be greater in some sense because we know when we flip to the negatives, I'm cutting that out entirely. That doesn't make any sense. Good morning, good afternoon, good evening, good night, good time, whatever it is where you are, whatever time it is where you are. Welcome to your Wednesday Math Minute, the only Math Minute guaranteed to be on Wednesday, guaranteed to be no more than 10 minutes long. I have something, I think, fun today. You can probably see on the screen. We have a little thing called the coordinate plane. So I want to look at how the two number lines we have studied previously for visualizing the scaling of multiplication. I want to see how those two number lines actually relate to the same two number lines of the coordinate plane. So we're going to be looking once again at this scaling function. We saw this the other day pop out of analyzing the distributive property x times k. So what can we say about functions that scale x by some factor and the different lines that they produce in the coordinate plane? So if I want to scale by some factor, I'm just going to take my number line and I'm going to redraw it so that any given item from the first number line matches onto a new scaled item in the second number line. So if I want to do a times 3 kind of idea, 1 is going to scale onto 3, which means that 2 would then have to scale onto 6, and 3 would have to scale onto 9. And of course, this scaling, this stretching of the number line works in both directions. -1 scales onto -3, -2 onto -6, -3 onto -9. And of course, as we said, 0 is special. It always scales onto itself. We don't have to do this times 3. We can do this times any number. That's the idea behind x times k. So the times k is going to scale more or less depending on what k is. When k is greater than 1, we're going to see that stretching happening. When k is less than 1, we're going to see that shrinking happening instead. But there was something I noticed when I did this. The way that the stretching or the shrinking looks kind of depends on the arbitrary distance just in terms of how I draw these two number lines. In other words, if I were to take this second number line and start to move it up or down, it's going to change what that scaling ends up looking like. If we move it closer, that times 3 idea, this is still the times 3 idea, kind of looks a lot more dramatic, right? It stretches out a lot more quickly when we move those two number lines closer together. So we try and reduce the things that are arbitrary when we're dealing with mathematics. We don't want there to be as many arbitrary elements as possible. We want there to be as few as possible. So I want to think about a different way we can draw these two number lines. Let's say that I take that second number line and I decide, all right, I'm actually not just going to randomly place it up or down. I am going to make it interact with my first number line. And we end up with what we call the coordinate plane. The coordinate plane is nothing more than two number lines placed perpendicularly to each other and intersecting at a special point we call the origin. Usually we let that be 0, 0. And that's going to associate an input of 0 with an output of 0. And now, instead of connecting those different lines at kind of an arbitrary distance from each other and visualizing multiplication that way, I can visualize multiplication a different way. Let's take our times 3 idea. So that means that we want, here, let's get rid of some of these numbers to make this a little easier to read. So that means that we want 1 to map onto 3 now, which would be somewhere around there. 2 should map onto 6. 3 should map onto 9. Things like, of course, 0 maps onto 0. -1 mapped onto -3, -2 mapped onto -6, and so on. And so I get a different relationship now. Instead of a bunch of different lines scaled a certain way, I have this one single line. In what sense is this fundamentally a times 3 idea right now? If you think about this one special relationship going through the coordinate plane, is this connection y equals x, or if we continue using function notation, f of x equals 1 times x. This just matches up every input with every output in a one-to-one way where they're always equal. So an input of 1 produces an output of 1. An input of 2 produces an output of 2. Input of 3 produces an output of 3, and so on. All of the k values that are greater than 1 end up living in this area here, where I am scaling that second number line in such a way that it's going to stretch this line upward. So something like y equals 3x would be analogous to this new function f of x equals x times k, where k is equal to 3. And so that's going to produce 1, 3, 2, 6, 3, 9. And so I get a nice steep line like that. If I wanted some k value that was between 0 and 1, I would end up with these more shallow lines because I'm taking my output and I'm making it a fraction of my input. And so it's causing it to be less steep. You can imagine, probably easily enough, another line over here, y equals negative x, or f of x equals x times negative 1, that simply relates every positive integer to its opposite, to its negative. So 1 corresponds to negative 1, 2 to negative 2, 3 to negative 3, and so on. Again, all the k values where it makes kind of a more shallow line would be between, I'm getting that backwards, would be between 0 and negative 1. And so that would be something like negative 1/2 times x. Finally, if we have some large negative value, something like, k equals negative 3, that's going to relate numbers over here, 1 to negative 3, 2 to negative 6, 3 to negative 9, and so on. So just an interesting connection I wanted to show you today. We can see this idea of scaling can be more effectively visualized using a coordinate plane, not just two number lines stacked kind of randomly with respect to each other, but specifically lined up at the origin at 0, 0, and then the scaling ends up showing up as steeper lines or less steep lines, and the reversal ends up showing up as lines that go down as we move to the right rather than up, 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 up as we move to the right. So I hope that's been helpful for you today. Make sure to like, comment down below if you have something you'd like me to do on a future Math Minute. Shout out to my notifications squad. You know who you are. And they told me to do a giveaway. So I'm going to do a giveaway of this amazing iPhone box. I'm going to give away this iPhone box to anyone who subscribes and comments. Let's just say on the next 5 videos. 5 videos! Probably will take us through the end of November. I will see you around.